So I like to solve a few additional problems using leading behavior. And then the last one here, I'm going to have you do, and we'll do it by a poll again. So C, B, A. I'll do A and B. So I'm going to do leading behavior on problem A. I'm looking only at the powers. Only looking at the powers. The biggest power in the top, 20x squared. Biggest power in the bottom, 3x to the fifth. So this limit is equal to the limit as x goes to infinity of 20x squared over 3x to the fifth equals, let's do some cancellation. Boop, boop. The limit as x goes to infinity of 20 over 3 times 1 over x cubed. And then we plug in infinity. 20 over 3 times 1 over infinity equals 0. How are you feeling about this, like, plug-in infinity nonsense that I'm doing? Leading behavior makes this problem significantly easier. Problem B is a problem that I think many students might get puzzled on this one. But leading behavior, I think, makes it very approachable. I'm looking at 36x squared and the next terms. Those are my leading behavior. I'm going to neglect the 7 and the 4. My square root is still going to be critical. This is equal to the limit as x goes to infinity of the square root of 36x squared over 9x. Nice simplification. Let's deal with that square root. Limit as x goes to infinity. 6 times the absolute value of x over 9 times x. But x is going to infinity, so x is bigger than 0. So the absolute value of x is equal to x. So this is equal to the limit as x goes to infinity, 6x over 9x, shwick, shwick, equals 6 over 9 equals 2 over 3. Pretty cool, huh? I love this technique. So now it's your turn. I'm going to let you do problem C, and I'm going to set up a poll while you're working on that. So go ahead and start working on problem C. We're trying to evaluate, use the technique of leading behavior. What's the value of that limit? Try circling. Make sure you have paper you're working on. This is very hard to do mathematics without paper. So write down the problem, circle the leading behavior, and then on the next step, write down what that limit is equal to. I'm going to go ahead and start working through this problem if that's okay. The leading behavior is determined by the highest power. 2 is bigger than a third. So the leading behavior in my numerator is the ax squared. In the denominator, 4 is bigger than the hidden 0 that's right there. So the 16x to the fourth term leads in the bottom. So this limit is equal to the limit as x goes to minus infinity of 8x squared over the square root of 16x to the fourth. Do some algebra. This is equal to the limit as x goes to minus infinity of 8x squared over, see, square root of 16 is 4. Square root of x to the fourth is x squared. Do some algebra. Cancel, cancel. This is equal to 8 over 4 equals 2. Asks a really good question. If you plug in the function into your calculator, what happens if you neglect terms? Let's do that right now. I think we should plot. Let's plot. Exercise. This is the word exercise. I'm an excellent speller, but horrible at printing. So exercise. Let's plot on one hand, 8x squared plus 7x to the 1/3 over the square root of 16x squared plus 6. And on the other hand, let's plot 8x squared over the square root of 16x to the, oh, that's the fourth, x to the fourth. So I think, is your question about the comparison of the plot of those two functions? Okay, let's plot them both. You got a calculator? I do. And I hope that you would do this along with me. Ooh, I have axes. So y equals, I don't think that's big enough. Y equals clear. Open paren, 8x squared plus 7x to the 1/3. Go right a few times. Divided by square root of, and the square root will act as my parentheses in the denominator, 16x to the 4th plus 6. And on the other hand, I want to just plot 8x 16x to the 4th. All right, so those are the two functions that I'm going to plot. Are you ready for us to plot them? Okay, so let's start with zoom 6. So the red one, okay, so I'm going to make that bigger actually. Okay, so check out the difference between those two curves. Here in fact we have the asymptote that the blue curve is approaching asymptotically. So the point is, and I'm going to transcribe this plot onto here so I can reason about it. The point is that I've got my blue curve, looks like it comes up and then it's doing whatever weird stuff it's doing, then it's doing that. And then I've got my red curve out here. And the point of doing leading behavior is that out to the right here, out here, the functions are about the same. And so I can treat one as the other. And that's what I mean by this statement right here. Right, when I state this, that I have circled in bold red right there, I don't mean that the two functions are equal to each other. I mean the limits are equal to each other. Okay, so I feel like this question really clearly illustrates this fact. These two functions, this one here and this one here, those are not the same. These are not the same function. It's the limits that are the same. And the point of doing leading behavior is that, like, in the point that we're curious about what's leading, we can't tell the difference between them. But over here, oh yeah, oh, they're super different from each other. We're only neglecting terms at infinity, way out here at infinity. And there is stuff that we can do for leading behavior to investigate what's going on near like roots and stuff like that, but that's not a subject I want to cover right now. So leading behavior is like the asymptotic case. And that was a really good point you made. Thank you so much.